Hello guys, hope you're doing well. My name is Mahmoud Kiasari from Special K and welcome to the new chapter of control. As you guys remember, for the previous chapter we talked a little bit about the foundation, what are the things that we are going to cover in this kind of series of videos, and today we are going to talk about the very first mathematical section of our control course. So without further ado, let's talk about it. As you guys remember, in the previous chapter, I told you that one of the steps that we have to consider in order to make sure that actually we are going to validate the work, because at the end of the day, when we were talking about the control system, we talked about the 6 steps. So one of the most important steps was about the mathematics. It means that we have to model our system based on the mathematics and make sure that everything is okay with that. Then we can some kind of work on the simulation, and after that we can implement it under real time. However, we cannot use all of the mathematical in the words. For instance, when we are dealing with derivatives and integrals, we do have a couple of issues. They are a little bit complicated. It takes a lot of time for the system in order to solve them. That's why we need another model. For instance, let's start our work with this. Let's start to work with a problem. So imagine that I do have the physical system, and this physical system, obviously I'm going to implement that. First of all, it requires the mathematical model itself. So mathematical representation of my physical model is going to be something like this. So UT is going to be your input. It could be anything. It could be just a pulse. It could be the linear part. It could be nonlinear. It could be anything. And Y is your output based on the time itself. So as you can see over here, everything is based on calculus. It means that everything is time domain. Obviously, it's complicated. I have to consider all of the factors, and it's not some kind of appropriate way in order to some kind of model my physical condition or physical works. That's why we are going to move to another one. Rather than talking about the time domain, we are going to talk about the frequency domain. And in order to do that, we do have a very good or very famous transformation that we call as Laplace transformation, which is going to act as a magic wand. This guy is going to convert derivatives into simple multiplication. So after using this guy, instead of just derivative to the power of 2, I do have s to the power of 2. Instead of just derivative to the power of 1, I do have some kind of just normal s. And instead of just normal y, I do have the ys. As you can see over here, I'm not going to work in just the time domain. I'm going to work in the frequency domain. And obviously, we do have some kind of definitions related to that. We are going to talk about it. So what was the issue again? The issue was that we cannot handle all of those complexity in the time domain part. That's why we are going to use the Laplace transformation in order to move from the frequency in the time domain to frequency domain. So a new language for control engineers is going to be frequency domain. So which is something called as an S domain, where system analysis becomes foundational algebra. The good thing about algebra is that imagine you do have two or more couple of systems back to back. Instead of just considering all of the facts or all of the algebraic conditions related to them, and in order to find the equivalent of all of them, you can use the Laplace transformation, and you can move to what? You can move to the algebra itself, moving from the calculus to the algebra, and then you can just multiply them, you can add them. The life would be way easier. So another important definition that we have to consider is something that we call as a transfer function. So transfer function is going to act as output. The ys is going to be output. Again, from now on, everything that we are trying to talk about is in S domain or frequency domain. Forget about the time right now. The ys, which is your output, divided by us, which is going to be your input. So what is the transfer function? Transfer function is going to show your system as a black box, and this black box or brain or whatever you consider can show you what would happen if you give this guy an input. What would happen to the output itself? You don't have to some kind of find a mathematical model every time. By just finding one time, you can have all of the information related to that. So GS is going to act as a black box, the US is going to be your input, and YS is going to be output. So again, what is the transfer function? It is the ratio of the system output to its inputs in what? In a Laplace domain. Why we use that? Because at this point, we are going to completely characterizes the behavior of a linear system entirely independent of what input is applied. That's a good thing. And the mathematical catch is that it assumes the initial conditions are exactly zero. So one of the important things that we most of the time consider in our work, especially in a Laplace transformation, is that we assume automatically our system doesn't have any initial condition. So if you guys remember about the derivatives and obviously integral, which is related to calculus, especially about integration, it is very important to know what is the initial condition of your system was. At this point, we assume that everything is going to start from flat. Everything is going to start from scratch, so we don't have that kind of initial condition. So again, try to think of the GS as a system fingerprints. It dictates exactly how the system will react to any kind of signal that are going to throw to that. So obviously, when we are talking about the transferring from the time domain to frequency domain, we cannot just do it naively. We have to consider a couple of facts. We have to know the language. We have to know the wording. We have to know the grammars. Then we can try to talk about that. Just before mentioning anything, I would like to say that f of s, which is something that we know in a Laplace domain, follows a simple, or I cannot say simple, it's a very common formula, that f of s is going to be integrate of f of t times e to the power negative s dt. It means that every time if you would like to convert one of your mathematical models, which is in the calculus, which is in the time domain, to the frequency domain, you have to follow this one. Obviously, try to solve all of our inputs based on that. It's going to take a lot of time. We don't have that time, but we would like to reach to the answer as fast as possible. That's why we do have a couple of rules that would be better to be memorized. So the very first thing is that about the time domain. If we assume that our input is impulse, or it's delta t, small, some kind of delta t1, so our s domain or frequency 1 is going to be 1. It means that it just acts as an initial k. If our input is the u, by the way, ut means that your output is going to be constant all the time. Your s domain 1 is going to be what? Is going to be 1 over s. When you have a ramp, when you have the linear condition, your output is going to be 1 over s to the power 2. When you have your exponential as an input, e to the power negative a or alpha t, your output is going to be 1 divided by s plus a. And if your input is going to be the sine of omega t, your output is going to be omega divided by s to the power 2 plus omega 2. And we do have the kind of same scenario for the cosine of omega t. But with this difference, that numerator is going to be s instead of omega, which we call this system as oscillation. So the grammar that we have to know about that is obviously we don't have this kind of inputs all the time. At some points you do have derivative, as you just saw before. So for the derivatives, the Laplace transformation of derivative is going to be s times f of s. What is f of s? F of s is the Laplace transformation of the normal f, which was the input, but at this point is derivative. And f of 0 means that the condition at the beginning, which we automatically assume we don't have any kind of initial condition, so this guy is going to be 0. Then we do have the integration. The Laplace of an integral of f of t times d of t is going to be f of s divided by s. And another important thing that I have to know is about the difference, or now the relationship between the frequency and time, is that f is equals to 1 over t, which is the very common formula. It means that when your timing is trying to reach to 0, your frequency is going to be trying to reach to the infinite and vice versa. That's why when we do have the limits of f of t, when t is going to increase and reach to the infinite, is going to be what? Is going to be a limit of s times f of s, while s is going to go to the 0. So we call it as what? It means that we are trying to work on the steady state, right? Steady state means that t is going to be infinite. And on the other hand, when you're talking about the initial values, the limit of f of t when t is going to be something around 0 or maybe more than that, we do have the limit of s times f of s, while s is going to move to infinite itself. Another important thing is that we have to see what is happening inside our transfer function. Why we are saying that? Because when we are talking about the controllers, obviously, the very first factor that you have to consider is that your controller, based on the input that you're giving to, is going to act what? Act as stable, unstable, it's going to be some kind of oscillation. What is happening exactly into your system? That's why we do have a transfer function. Transfer function is not just a nice guy try to give you the output divided by input or try to give you a fingerprint of your black box. Transfer function is there in order to give us some of those information that we call it as a poles, it means that obviously g of s is ys divided by us, and at the end of the day you have some kind of fraction, and in your fraction you have the numerator and you have denominator. So obviously your denominator, we have to make sure it cannot have all the numbers that we need, because as you know, in a fraction, when your denominator is 0, it means that your fraction is undefined. So by putting that denominator to equals to 0, or finding some numbers that we call as poles, we can draw them in a plane that's something we call as S-plane. And S-planes, again, in S frequency, or in the frequency domain or the S domain, is a very important part. We are going to talk about it a lot. But put it inside that plane, we can understand what is going on inside our system itself. On the other hand, we do have something that we call as zeros. Zeros means that at what point your system is going to be 0. So obviously, by just putting the numerator and just moving it and making it equal as 0, we can find some numbers. By having those poles and holes, or poles or 0, we can completely understand that what would happen as when t at the end of the day, or when t is going to reach to the infinite. What would happen as a steady state situation? And my system is stable, it's not. How I can do some kind of something that we call as a compensation, which we will talk about it in the final stage. And what are actually the behavior or the characteristic of my final model. So that's why, as you can see over here, we do have something we call as a S-plane. So S-plane, it has the left side and it has right side. The left side is the one that we like. It means that if your poles, or something that we call as the DNA of the system, can be located on the left side, we can say that the system is stable. Or when we do have the zeros on the left side, we can say something about the system itself. So left side is the one that we like, while the right side is somehow the part that we don't need, or the part that we don't like, because at the end of the day, if your poles is going to be on the right side, you do have oscillation, or you have an unstable system. So let's talk about it again. Let's just recap everything. As I just mentioned, we do have poles. So this guy is going to be the denominator roots. So this one is going to determine the system's core model. Their location dictates stability and response speed. So whenever we are on the left side, means that the left side, again, we are talking about the S-plane. So S-plane is going to be just a normal plane that in the previously we had some kind of X and Y, but at this point we do have some kind of real axis and we do have the imaginary axis. So the real axis and imaginary axis is going to be based on your poles and zeros, because obviously when you're trying to talk about the system, for example, the second order system, obviously you are dealing with s to the power 2, and not all the time the roots of your nonlinear equation is going to be just real numbers. Sometimes they're imaginary numbers, as you all know about that. So these imaginary numbers, they need a place in order to be located. That's why we do have the S-plane. So if you are some kind of poles and going to be on the left side, it means that your system is going to be stable at the end of the day, while if they are on the right side, we do have an unstable system. So the key terms about the poles is that they are system modes, and about the stability and the speed, or a DNA of your model itself. On the other hand, we do have the zeros. So zeros are going to shape the response profile, affecting exactly how quickly the system is going to react. So obviously, you guys remember we talked about the settling time, and we talked about the rise time. So these kind of concepts are related to the zeros of your transfer function, which we call as a GS. So it means that they're going to talk about the response and the reaction speed. And what are the insight? An experienced engineer can look at just some kind of poles and zeros and plot and instantly read how the system will behave without solving a single equation. By having this visualization, you are going to have a very big picture of the idea of your system itself. And before doing any kind of calculation, you do have some kind of perspective of what is happening at the end of the day to your system. So let's talk about some kind of example, some kind of electrical example, some kind of mechanical example, physical or mechanical examples related to our system, and how we are going to use the time domain or convert it from the time domain to the S domain itself. Imagine that I do have the circuit diagram. As you guys know from the electrical circuit, as we just talked about it, or from the college or from the university itself, I do have the voltage source, I do have the resistance, and I do have the capacitor. Imagine the V out is going to be the voltage of capacitor itself, while Vn is just your source. So Vn So sorry, something happened and the video wasn't recorded, so I have to start again from scratch at this point. So again, at this part, I talk a little bit about what is going to be about my some kind of circuit diagram, or we are talking about the normal example of the time domain and then how we can convert it to the Laplace one. So as you can see over here, I do for my circuit diagram, I do have my voltage based on the KVL. We know that the voltage of input should be as the same as the voltage of R plus the voltage of C. So Vn is going to be the what of the voltage of your resistance based on the Ohm's law, in that V equals R times I, while the I is actually IC. It means that the current that goes through your resistant is the same as the current goes through your capacitor because it's series condition. So IC, we know formula for that. IC is equal to C dV divided by dt. So based on this one, put it over here, and we know that the output is VC. We do have this formula. As I just mentioned, we don't like it that much because we have to deal with derivatives and it would be a little bit complicated. So we are going to move from the time domain using the Laplace transformation to the S or frequency domain. So your Vn is going to be Vn over Vn based on the frequency, your Vout is Vc based on the frequency, and your RC dV divided by dt is going to be RCS times Vc. At the end of the day, the GS, which is going to be your output divided by input, is going to follow this specific formula itself. And as we know, in order to find the pole location, the only thing you have to do is you have to make your 1 plus RCS as 0. So S is going to be negative 1 over RC. So the time constant, or amount of time that it takes for a capacitor in order to reach to 63% of its maximum charge, is something that we know as RC. And at the end of the day, the DC gain is going to be 1. So this is something that we call as a first order circuit or the first order system, because we only have derivatives to the power 1. But what would happen if we do have the derivative to the power of 2? So at this point, we do have another scenario. It means that rather than just the C or capacitor and R resistor itself, I do have the inductor. Anything would be the same for C and R, but we do have another one, which is the inductor itself. And the inductor is going to follow this formula. The voltage of inductor is L times di divided by dt. Di again is dic. So if you put it over here, rather than just derivatives to the power 1 or the first order, we do have second order. So at the end of the day, your formula is going to be like that. And if you find your GS, or if you find your transfer function, it's going to be something like this. As you can see over here, our system got a little bit complicated because rather than just having one root, we are going to have two roots, and it doesn't necessarily say that those roots are going to be real. So at this point, we need the S-plane, and we need to locate them in order to understand what is going to happen to our system in long run. So as you can see, the poles are going to be two poles, and often they're complex. It means that they got the conjugate. Then we do have two other concepts or two other definitions. The very first one is a natural frequency. So natural frequency in a system, which would be showed with radian per second, or at this point we do have 1 divided by root of LC, is going to show at what frequency your system would oscillate if you don't have any friction. Imagine that you're just going to punch some kind of the boxing bag. If there is no friction, that guy or that specific your system is going to just move back and forth by itself with this specific frequency. On another hand, we do have another thing that we call it as damping ratio. What is the damping ratio? Damping ratio is the level of friction, and it shows that how system is going to have resistance against the changes. At this point, we show it by this because it's just a ratio. It doesn't have any unit measurement. So when we do have these two ones, the natural frequency and damping ratio, we do have a very good some kind of idea of what would happen to the system. And obviously, when we do have the poles, we can just locate them on the system to see that actually where they are. If on their left side, the system is stable. In the long run, if they're on the right side, vice versa would happen. So let's talk about the mechanical aspect. So some kind of this point, imagine that I do have this guy, and I do have obviously there's going to be the force, and I do have mass, I do have the K, and I do have the B, which is going to be related to whatever some kind of component is connected to my mass. Based on the time domain system, we know that the md to the power 2 of x divided by dt2, by the way, x is going to be distance, plus b dx divided by dt plus kx is going to be F, your force. And the GS at the end of the day is going to be something like this. So as you can see, this guy is very similar to our some kind of the RLC circuit. On another hand, we do have another physical system, and at the end of the day, if you do that, you still see that we are dealing with the second order system, but the coefficients for s to the power 2 or s to the power 1 are going to be a little bit different. What I'm trying to say is that this pattern is identical, and understanding only one means of one of those examples automatically is going to give you understanding of all of those systems. At some points you do have your resistor, and another point you do have mass, and another point you do have other things. But at the end of the day, all of them are the same. So by finding the poles, you can find the stability of your system. And this is the very good some kind of comparison or table related to them. For instance, when we are talking about a mechanical domain, we do have force, while we do have voltage on an electrical domain. When we are talking about velocity, we are talking about the current. When we are talking about the displacement or the distance, we are talking about the charge. When we are talking about mass, we do have the inductance. When we do have the damping, we do have the resistance. And when we do have the spring, we do have the inverse capacitor itself. So at the end of the day, it says that your systems are going to act identically. The only thing that would change are the things that are related to that. For example, the force, the voltage, or whatever you have in your mind itself. So let's talk about the modifiers and sensors. Let's talk about other examples. Imagine that you do have two gears that are going to be connected side by side. We do have the smaller gear that has N1 number of teeth, and we do have the bigger one that has N2 number of teeth. So this one, obviously, you just saw a lot in any other kind of application. The reason that we do have this guy is that whatever load that is going to be connected to the second one, it needs a less amount of energy for the first one in order to move that. But how we can decide how much energy can we do we need is going to be based on a very important number that we call as a gear ratio. The gear ratio is the number of teeth on the second side over the first side. It means that wherever your N is going to be bigger, then some kind of amount of energy or effort that you have to have in order to move something is going to be less. How? The J equal, or the inertia for moving a specific load is going to be J load divided by N to the power 2. Obviously, when your N is way bigger, your N to the power 2 is also going to be bigger, and your J equal is going to decrease. It means that you need less amount of energy to move that specific thing. On another hand, we do have the DEQ, or we do have the damping. So when your D load divided by N2, the same thing is going to happen. Not only we can move it faster, but we also can stop it faster. On another hand, we do have another concept, we call it as potentiometer. So potentiometer is going to act as a variable resistor, or we can just call it as a sensor. It means that based on the number, or based on the angle that actually we can have, we can call it as the theta divided by theta max that we joined at 360 degrees, we can decide what would happen to our output voltage, because input reference is something constant, and the output is based on the two numbers, based on only one numbers. So it would be the theta divided by theta max. At this point, your some kind of transfer function or your system, it just act as the constant number, right? Another important thing that we have to know is how we actually can use the system itself. Because so far when we were talking about the Laplace one, the Laplace was good if our transform function only works in the linear systems. Obviously, reality doesn't say that, because reality has frictions, it has saturation, it has hysteresis, and it has so many other kind of things. In order to do that, for example, this is going to be my reality, and as you can see, it's completely nonlinear. But if I would like to use the transfer function, I have to find a way in order to convert it to the Laplace, or use the Laplace one. So there's a concept, or the cheat code, that we call as a linearization. What does it say? It says that instead of just looking at the whole scenario, or how the whole real world as the way it is, we can try to look at it or zoom at it at a specific point. If you zoom at this point, you can see that this guy is somehow acting like a normal line, or it's linearized. It means that my math just converted to what? My delta y is m times delta x, which is going to be a normal formula that we do have based on the slope, based on the input, and based on the output. So I do have my m, but at this point, instead of delta, I'm going to call it as d, or derivative. So which is going to be my operating point. If you do have some kind of example, for instance, pendulum, the nonlinear formula is t is going to be negative mg times sine of theta. But If I can consider the theta or angle is very small, I can say that I'm working in the linear mode. So as long as we keep our controller operating in this some kind of zoom in or small signal or linearized window, then we can say that our transfer function is going to work perfectly. We are going to see that a lot in the future, but this is something that I would like to talk about. As you guys remember, I told you that one of the most important thing about converting the time domain to frequency domain is about the combination. Because when you do have two systems or more, and when you're trying to work them parallel or when you're talking them in series, and if you would like to find the relationship between output and input just by focusing on calculus, is going to be way complicated. That's why we use the frequency domain, and that's why it's going to show its privilege over here. So at this point, when I do have two series or some kind of the cascading model of my controller, because obviously we don't only have one controller, so we do have what the total transfer function is going to be G1s times G2s. On another hand, if you do have them in parallel, we are going to add them up. So I just told you, block them algebra lets you take the massive complex system and reduce them into what combination of simple manageable mathematical pieces, and this is one of the important essence of converting the time domain to frequency domain. Let's have another some kind of example of that. Some could call it as a masterpiece, that how actually your motor or some kind of motor in the electrical world is going to work. So as you guys know, the motors means that I have to inject the voltage and I have to get some kind of speed on the output side. So the voltage input is going to pass through different kind of systems. The very first one is just the amplifier. It means that my input voltage is going to be amplified. Since it's just amplified, my system is going to be just Ka. Another thing that I have to know is about the G of motor or the control system itself. It is the first order, so the formula related to that is Km, which is again there's related to about the speed and voltage, means that based on each voltage you are going to give your motor how much your speed is going to increase. Then we do have something we call as Tm or some kind of tau, which means that how long does it take for my system to reach to time speed, and it's going to follow this formula. Then we do have the integrator. Why we don't have in this integrator? Because at some point I would like to know the speed, but at some point I would like to know the position. That's why if I would like to know the position, I'm going to use 1 over s. And finally, we do have the tacho generator. So tacho generator is something that's optional, sometimes it's not there, but this guy again is just act as the gain itself. So at the end of the day, my G total is going to be something like this. If we don't consider the tacho generator, obviously you completely understand how we found it out by just multiplying by this guy and finally by this guy. Since we don't have it, we are going to ignore that. That's the beauty of the Laplace transformation or frequency domain. Another thing that we have to know, and probably we are going to see it a lot, is at some point we don't have that much of information about my system, and my system is just a black box. So how am I going to understand the transfer function? It is simple. The very first thing that you have to do is just give it a very some kind of arbitrary or very some kind of normal input, for example the sine wave, and then you by reading the input and output is going to give you two important information. The very first plane that we are going to see it a lot is about the magnitude versus frequency, and we show the magnitude based on decibels rather than a normal thing. You will see why. And another important one is about the phase versus frequency. By knowing these two guys, I can have a very clear idea of what is happening to my transfer function. By knowing the information about this and this, I can draw that. So the result is that the empirical frequency response reveals the hidden poles and zeros, and allowing us to curve the fit and data and work backward in order to understand the GS or the transfer function. So at the end of the day, we talked about the concept of why we use the Laplace transformation and why we don't like the time domain that much. As you just saw, whenever we are dealing with much more complicated system, whenever we do have them side by side, means that situation is getting a little bit out of hand or out of control. That would be better in order to move from the time domain to the frequency domain, because everything is going to be way simpler. So for the next slide, we are going to to talk more and in detail about all of these aspects. Again, we are trying to touch the basics. We don't try to talk much in detail. As you just saw, we had a couple of examples, but I didn't give you that much of information because I don't want to give you some kind of misunderstanding and confusion. At the end of the day, we would like everything to be smooth. We would like to move in a very manageable pace. Thank you very much for being here with me. My name is Mahmoud Kiasari. I would be more than happy if you share, comment, and like my videos. That would be so helpful for me. Have a super great day, night, whatever. See you around.